All right, so welcome to class 65. We're going to measure and calculate period and frequency. We're going to construct some waves, and we're going to identify nodes and antinodes. So the period of a wave is the amount of time it takes a particle on the wave to return to its original position. So it's like the time to go up and down or back and forth. So if we're talking about a pendulum, let's say, it's the time it takes the pendulum to go all the way across and all the way back. In the image here, the period is 0.4 seconds. You could just look at it like a wave, crest to crest, 0.4 seconds. The amplitude is the distance from equilibrium, so that's 0.2 meters. Now frequency. We have an equation that relates frequency to period. Period is equal to 1 over frequency. So if we're given the period, we have 0.4 seconds equals 1 over frequency. Cross multiply. Frequency is 1 over 0.4 seconds. Comes out to be about 2.5 hertz. So what is a hertz exactly? So 1 hertz equals 1 oscillation. Some people like to use the word cycle per second. We had created a displacement versus time graph in class for a pendulum. That's something you're going to have to get from one of your classmates, but we'll do plenty of other wave constructions. So this wave construction says a wave traveling through a uniform medium has an amplitude of 0.2 meters. So we'll highlight that. And it has a wavelength of 0.4 meters. Right, so that was the amplitude. And a frequency of 10 hertz. So what we're going to have to do is we're going to have to draw one complete wave cycle. So one thing to keep in mind here is that on the y-axis we have displacement, on the x we have position. So we're not graphing time or frequency, period, any of that at all. We're only graphing amplitude on the y and wavelength on the x. So here's how I like to graph these. I like to mark off first the beginning of the wave and the end of the wave. I like to mark off the halfway point. And halfway between the beginning and the halfway point, I like to put the amplitude, so that's 0.2, so I like to put that right there. And halfway between the midway point and the end, I like to put the trough there, the other amplitude. Then you just fill it in. Now you don't have to draw it curved. If you'd like, you can kind of triangulate it. You can draw just like straight lines. That's perfectly acceptable. Now it says here, in a different color, draw a wave with the same wavelength and twice the amplitude. So let's change color. Let's go to like blue. All right, so twice the amplitude. So it's going to start and end at the same spot. So our midpoint is the same. But instead, it's going to go twice the amplitude. So the new amplitude is going to be 0.4 meters. So it's going to go all the way up here and all the way down here. So this one's a little hard to draw curved, so I'm going to just kind of draw some straight lines. Okay, so the wave looks kind of like that. Okay, the thickness of the lines doesn't really matter as long as you get the right shape. The next one here says on the centimeter grid, so that means that each of these boxes is 1 centimeter by 1 centimeter. Draw at least one cycle of a periodic transverse wave with an amplitude of 2 centimeters and a wavelength of 6. So I'm going to draw my 3 dots to start, one at the beginning, one at the end. So I'm going to count 6 boxes, 1, 2, 3, 4, 5, 6, and one at the middle. Has an amplitude of 2 centimeters, so it's 2 boxes up. So I'm going to go between the first and second dot, and the second and third dot, and I got my nice wave here. Okay, it doesn't have to be perfect as long as you get the idea. Now it says in a different color, sketch a wave with twice the wavelength and the same amplitude. So if it has twice the wavelength, that's going to be 12. So here's my beginning. Here's my middle now at 6, and I have to go another 6. 1, 2, 3, 4, 5, 6. Same amplitude. So the amplitude is going to be between the first and second dot. The next dot we're going to draw is between the second and third dot right here. Again, the amplitude is 2. And our wave looks something like that. So let's keep it going with the colors here. So we're going to start talking about standing waves. So a standing wave is made when two waves moving in opposite directions interfere with one another. See the image to the right. So these are classic images of standing waves, okay? We saw a lot of those in class. Now, one thing to emphasize here is that standing waves created when waves interfere. We'll get more into wave interference later, but just realize that it's due to wave interference. So there are two parts to note on a standing wave. So the first part is the node. That's the part that doesn't move. That's actually where destructive interference takes place. One way I remember this is that nodes, no, move. And then the antinode is has the largest displacement. I usually think antinode, I think the A for amplitude. So how many nodes and antinodes are in the diagrams below? So this diagram has a node here, here, and here. So those are 3 nodes. And a lot of people might think that this one has 4 antinodes, but these are each actually 1 antinode. Okay, so this one only has 2 antinodes. The next one, let's see how many nodes it has. It has 1, 2, 3, 4, 5, 6, 7. And we're always going to have 1 fewer antinodes than nodes. So there's going to be 6 antinodes. And you can count it off. 1, 2, 3, 4, 5, 6. So these are just some old Regents questions about nodes and antinodes. So this one, the antinode is at point B and D. And the nodes at A, C, and E. This question says, how many antinodes are shown in the diagrams? So there's going to be 1, 2, 3 antinodes. And there would be 4 nodes in this one. So hopefully this video helped you out. Don't forget to hit the like button and subscribe to the channel.